Hello, everyone. We're working on Chapter 12, Part 1, An Introduction to Statistical Methods and Data Analysis by Ott and Longnecker. In this chapter, we're going to be discussing multiple linear regression, model, and parameter estimates. All right, example. Survey of yearly salary of beginning programmer / analyst. A survey of information systems managers was used to predict the yearly salary of beginning programmer / analyst in a metropolitan area. Managers specified their standard salary for a beginning programmer / analyst, the number of employees in the firm's information processing staff, the firm's gross profit margin in cents per dollar of sales, and the firm's information processing cost as a percentage of total administrative costs. Let Y equal the salary, X1 equal the number of employees in the firm's information processing staff, X2 equal the profit margin, X3 equal the IP cost. So essentially, we can set up this model such that we have Y equaling beta 0 plus beta 1 X1 plus beta 2 X2 plus beta 3 X3 plus epsilon. All right. In this case, we have three variables. So essentially, we now have an intercept, that's our beta 0. And then beta 1 is the slope associated with the number of employees in the firm's information processing staff. Beta 2 is the slope associated with the profit margin. And beta 3 is associated with the IP cost. The epsilon is the random error. All right, after we're done, then we can fit the model, and we're going to get Y hat equals beta 0 hat plus beta 1 hat X1 plus beta 2 hat X2 plus beta 3 hat X3. And so if we knew the number of employees in the firm's information processing staff, the profit margin, and the IP cost, we could then estimate the salary, the starting salary of the beginning programmer / analyst in that particular metropolitan area. All right, another example. A student working for a campus apparel shop wants to study what factors might contribute to customer spending. All right, let Y equal the dollars of sales per customer to date. Let X1 equal the monthly allowance received by the customer, X2 equal the number of years in college for the customer, and X3 be gender. All right, we could fit a few different models. In model 1, we have Y equals beta 0 plus beta 1 X1 plus beta 2 X2 plus beta 3 X3 plus epsilon. So in this case, we have an additive model where each of the variables shows up once in the model. And once again, remember, beta 0 is that Y-intercept. Beta 1 is the slope associated with the monthly allowance received by the customer. Beta 2 is the slope associated with the number of years in college for the customer. And beta 3 is the slope associated with gender. So once again, if we want to predict the dollar of sales per customer to date, we can use the estimated Y-intercept, beta 0 hat, plus beta 1 hat X1, the monthly allowance received by the customer, plus beta 2 hat X2, the number of years in college for the customer, plus beta 3 hat X3, gender of the customer. Okay, similarly, we could fit an interactive model. So model 2 is an interactive model where instead of just having beta 0, beta 1, beta 2, and beta 3, we're going to have beta 4, which is a transformation of X1. We're going to have, beta 4 is the slope estimated that we're going to estimate associated with a transformation of X1. So once again, I'm going to say that one more time. Beta 4 is the slope associated with a transformation of X1. Beta 5 is the slope associated with an interaction term, X1 times X3, and beta 6 is the slope associated with another interaction term, which is the interaction between X2 and X3. So if we were going to write this model out, we'd actually get y hat equals beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2 plus beta 3 hat x3 plus beta 4 hat, in this case x1 squared, plus beta 5 hat x5, which is just x1 times x3, plus beta 6 hat, and then we have x2 times x3. So this is what our prediction line looks like. So now we don't just have one x, we have many x's, and we have a single y. All right, so we've written out model 2 in another way. So remember, if we're thinking about the true value of y and the true value of x's, we have some random error associated with it. But once we have our estimates for all our betas, then the y is also an estimate. So given a particular set of x's, we can actually find a prediction for y. And we're going to use the estimated slope coefficients, beta 0 hat, all the way down in model 1 to beta 3 hat, and in model 2 from beta 0 hat to beta 6 hat. Okay, note that we're linear in the betas, so we're never allowed to raise a beta to a power, but we are allowed to raise x's to a power or have the interaction terms like we have here, x1 times x3, x2 times x3. We have x4 equals x1 squared, but notice that beta 4, that beta 4 hat, that does not have a power on it. So we always say that in linear regression, we are linear in the betas.